send you guys the homework set for belief space planning. It will be about 3 questions and they'll be due in a week. Okay, I'll send this at the end of this class and it will be due next week. And then if I might add, I think then that would just leave the reinforcement learning and the last topic which we're going to do, which is statistical learning. Okay. And then I just returned the homework set 2, and then the mini project would be returned soon. I think probably next class, and then of course. Okay, so today I'm going to be doing the reinforcement learning, the chapter for that is chapter 20, and actually you should just read the chapter. It's you should be able to make sense of what's going on in that chapter. If you don't, then you didn't really keep track of MDPs and POMDPs. POMDPs is less important, but MDPs is definitely important. Okay, there is an aspects of learning discussion that is there that, especially Bayesian learning discussion, that might, if you are not familiar with Bayesian learning, it will become clearer when we get to statistical learning. We'll talk a little about it today, but not much. Okay. So in reinforcement learning, the basic idea is until now we looked at MDPs and POMDPs as an inference problem. That means the reward model is given, the transition model is given, and so really you don't need to try it out in the world, because if you know that when you try it out, that's exactly what will happen. Okay, it's very important to understand that even when you have a stochastic model of the world, that's knowing how the world works. Okay, because the probabilities tell you that exactly 30% of the time when you do this action A1 in state S1, you will get into S2, and the 70% of the time you get into S3. That's the maximum knowledge you have. Okay, so really there is no advantage of doing it in the world and then figuring out what is the best action to do. So you should be able to just think in your head. So planning is possible because the entire model is there. And so the question then is, what if the model is not available? And what you have to do then is learn so in some sense you are asked to do well in the world without being given the model of the world. So you would hope essentially that as you keep executing in the world, you do various actions in the world, and presumably you have what you have going for you, of course, is your effectors and your sensors. Okay, so you can actually affect the world and see what, do an action and see what happens. And see what happens is the sensing aspect. And then an extremely important part is you have memory. Because if you don't have memory, then every time you do this, then it's completely new. Okay, so presumably as you act in the world for a while, the question is, could it not have been possible to learn all the, to actually get to a point? So suppose your friend has been given the model of the world. You have not been given the model of the world. And you both have been given infinite amount of time. Could you ever reach the performance that your friend has starting? Okay, in the very beginning itself the friend has the model, so they can do the optimal policy with respect to that model, and then they'll be getting the highest performance. You will be slowly learning the model. The question is, can you ever reach optimal performance? Okay, that's what reinforcement learning is trying to handle. Okay, so the underlying model of the world itself is, you still think of it as a set of states and a set of actions, and the model of the world that you're missing is the transition model. You know what actions you can do, you have effectors, but you don't know what that action will do to the world. Exactly how often when you do this action in S, you'll get to S dash. That you don't know. Okay, and there is this other issue of reward function. Just a second. Reward function, and that too is not given to you. But the point, of course, is when these are supposed to be, remember the reward function is supposed to be immediate rewards. So you should have been hardwired to observe the rewards. If not, you're in trouble. Okay, if you came into this world hardwired to observe the rewards, And then when you actually reach a state and that state gives you a reward, you can feel it. And if it's good reward, you want to do more of it. If it's bad reward, you want to avoid it. Okay, so there is an interesting issue as to, in fact, we assume full observability. In doing this, we assume that we have effectors and we have sensors, but we have full sensors. That means essentially the sensor will tell you which state you are in. But you also need reward sensors. You need to be able to, feel the reward. Okay, we'll just assume that is possible. That's the way it's happening. Okay, but in general, actually, there are quote unquote depressed people. It's not that the world is giving them less reward than it is giving to you. Depressed people have lost the ability to experience the reward. So it's the reward circuitry that's messed up. Okay, and then when you take drugs, then you don't even have to do anything. You're getting lots of reward, free. Right? And so you almost don't have to do any action. It's like, basically that's the interesting evolutionary connection. Reinforcement learning is full of all sorts of beautiful connections to real life. So there had to be some way in which we can sense rewards, right? And then so we have this dopamine system in the brain. And then of course, there are natural highs that you get after achieving some A+ grade, you get a little piddly dopamine. You can get crack cocaine and you can get a huge amount of it right away. So you don't need to do the exam. Okay, but we'll not get into that. We'll essentially say that the rewards can be experienced. But when you get there, and once you get there and you experience the reward, since you have memory, you can then remember that next time you go to that stage, you will get the same reward. Okay, so of all the things to be learned, reward learning is the easiest because you just remember, if you go to this state, you get this reward. Yes, there was a question.
You mentioned that the goal is, or one of the questions is whether we can learn an optimal model.
No, actually, so I'll give you the formal specification just in the next slide actually. So we'll get to that, what the objective of RL, reinforcement learning, is, and then you can ask me a question again if you have. Okay, so there are, of course, reinforcement learning has been studied in psychology. It's also been, there are applications of it. In fact, one of the first AI systems is this Backgammon system, which essentially learned a very good value function for TD Backgammon. And then that was enough to actually beat the humans. Okay. Actually, in fact, this one is a more recent one. This is Tessaro's. But early on, there was Checkers program. One of the very earliest machine learning programs was the Checkers program by Samuel in 40s and so on. And that too essentially used the ability to do the reinforcement learning. Okay. And the thing that you want to understand is, in the case of reinforcement learning, normally you don't have a model of the world, so you cannot simulate. The difference between planning and acting is, in planning, nothing, the world doesn't change. You just, simulating the various changes to the world. If I do this, this will happen. If I do this, this will happen. I don't like this, I like this, so I will do this. That's what planning is. If I don't have the model, then I have to do it in the real world. And if in fact the bad thing happens, I die. Okay, so one very important thing, of course, is reinforcement learning won't even be possible unless there is ergodicity in the environment. And one other interesting thing, actually, philosophically speaking, is because we have invented not only memory, we invented persistent memory. So if I send you and you fall into the canyon, and then you cry saying, "Oh my God," and I don't hear from you again. I learned something. You don't learn. You're out. But I learned something. So I get to write in my book. It's not a good thing to jump into the canyon. Okay. So this multi-agent aspect also helps, so that we are essentially, even though the real world is actually non-ergodic, some poor souls, go away. And remember, Benjamin Franklin had people holding up kites into the lightning. And the people who held the kites are no longer there, but he got to write papers. And so, he is alive. Okay. So anyway, we sort of assume that if it's a single agent scenario, if it's not ergodic, you're dead. You can't learn. Okay. So, let's see, where is my objectives? This is the first slide and that's the second slide. So what's the objective of a reinforcement learning algorithm? Okay, so if you think that an MDP is the model of the world, that means the world is essentially having, so you have actions and you get to learn what the state is. As soon as you are in the state, you get to learn what the state is, and each state gives you a reward, immediate reward, that you are equipped to sense right away, okay, fully observable. So then, given you have effectors and perceptors, and you have the world in which you can do these things, and sometimes if you are lucky, you might also be given a simulator instead of the real world. This is actually a special case. Oftentimes only these two are available, but like for example, rather than put people, get pilots to learn how to do flying on real 777s, we build very effective simulators. Okay, and they almost, the thing about the simulator is the simulator gives them back all the feedback, almost all the feedback the world would have given. The usual, the increasing G's and crying in the background when your flight kind of takes a dip because the passengers are falling off and so on. All that you learn, and then with respect to that, you can essentially almost feel as if you are in the world, except it's ergodic because when the simulator dies, you can restart, you can reset the world. Okay, and furthermore, one of the very interesting things about the simulator is you can replay the same future again and again and again in a simulator. In the world, you don't get to do it, because especially in a stochastic world, if you do this and do this and do this, something happened, let's say last time. When you do the same things again this time, something else might happen. Why? Because the actions are stochastic. Okay, there could be very rare outcomes of an action that just happened once, and you are unable to reproduce that, and so you don't get to learn much about that easily. Whereas if it's a simulator, all you need to do is keep the random numbers the same, so that you would get the exact same sequence of states, and so you can learn with respect to that. So the general reinforcement learning is just those two, but sometimes you have a shortcut for reinforcement learning where there is a simulator. And one of the interesting things you have to learn as we go along is the difference between a simulator and a model. Okay, a model is what the pilot gets into their head. If they are an experienced enough pilot, they don't actually have to do the bad maneuver and hear either screeches or simulated G-forces. They can feel it, they can simulate it in their head. That would happen. That's a model. A simulator is just a stand-in for the world, which kind of directly gives you the same perceptions that the real world would have given, so that you can learn with respect to that. Okay. So anyway, if these are given, then what reinforcement learning is asking you to do is just learn how to perform well. So to some extent, actually, reinforcement learning is AI complete. It's not just AI complete in the sense it's the hardest AI problem, but it is AI, because that's what an agent is supposed to do. I have a couple of things I can do to make the world change. I can, sense the world, and I have these rewards that I can feel. So the perceptors include reward perceptors. Okay, and then all you do is do better. Okay. Now, if you have this MDP model, then you can actually talk about a formal definition of what does it mean to perform well. It's essentially, if you are following some policy, then I want to consider your average cumulative reward that you got. Okay, average cumulative reward you got, and if you have high average cumulative reward, then you're doing well. Otherwise, you're not doing well. Okay, the average is important because it's stochastic actions. So sometimes the right things will get you the wrong states, and sometimes the wrong things will get you the right states. Okay, sometimes you can cross through the red light and all that happens is you go home faster. Okay, that's exactly a wrong thing which actually gave you the right state, and you don't want to learn, so you don't want to learn based on that crossing red lights is always a good idea, because one day you'll cross and hit somebody or you get hit. Okay, so all you want to do is learn to perform well, which is average expected reward over long term average expected cumulative reward. Okay, an average being expected anyway. So long-term expected cumulative reward. Okay, that's what you want to maximize. Now, that's all that matters really. Everything else is details. Okay, so if you're doing extremely well, then all I can tell whether or not you're doing well. You, the agent, is doing well. I can tell as an outsider whether or not you're doing well. Okay, now how you are doing well is the algorithm that you're using. To be able to understand the algorithm you're using, I have to do lobotomy and see actually what are you doing to show this great performance. And there are a variety of things you might be doing. And ultimately all that matters is this is what you want to achieve, but this is the end, and these could be some of the means to the end. Okay, in fact, if you want to learn to perform well, really what you should be doing is just directly learn the policy. Assuming you know the goals, which also is not obvious, but assuming that you know the goals, assuming you know so you want to just learn an optimal policy for the underlying MDP. And once you learn the optimal policy, then I would be impressed with your performance. Okay, so that basically means just directly learn the policy. But then the entire MDP literature has told us that policy is connected to value function. Okay, so you could, for example, learn the state values directly. You could be possibly learning just the state values directly. And you're using that to convert it into the policy. Now, if you're learning state values and you're converting it into the policy, right, then the question, of course, is if you want to convert it to the policy, then you need a transition model. Because if I just tell you this is a good state, this is a good state, this is the total value of this state, this is the long-term total value of this state. Okay, you are in the current state S1, whose value is like 75. And here are all the maximum values, long-term values of all the states around you. Does that help by itself? Not really. You need to do an action to get into a good state. That's what you're interested in. So you have a bunch of actions. You don't know what those actions do. Right? So there are two ways of going from the state values to the policy. One is the one that you know all along, which is having the transition model. So if you happen to have also learned the transition model of the actions, right, then essentially you do the action that gives the maximum expected value. Okay, so you needed to be able to do it this way, you needed to have learned the transition model. Another way is, if you don't want to learn the transition model, it turns out that you can, instead of learning the value of the state, instead of learning the state value, you can learn state action value. Okay? A state action value essentially is, it's basically called the Q value. Okay? Q of SA. That means if I'm in state S and I do action A, what is the value I get? What is the maximum long-term value I get? Okay, now the interesting thing, of course, is Q star of S and A is related to V star of S, because this is nothing but max over A of Q star of SA. So a state's value is really the value of its most promising action. Do you see this? Q values are nothing but you're taking the state's value and splitting it into state's value if you take this action, take state's value if you take this action, state's value if you take this action. And if you can take 4 actions, then whichever is the most promising action, that's your value really.
It's expected value of performing this action.
No, because you are an agent, you know which action to pick. Once you happen to know the Q values, once you happen to know the Q star values, so I tell you that you are in the state S, you can do A1 or A2 or A3. If you were to do A1, the maximum expected reward that way would be 70, A2 50, A3 40. Which one would you do? You'll do A1. So you just basically, this is where you are taking the max. The advantage of this formulation, it turns out, is if you think in terms of Q values, then if you learn Q values instead of the values of the state, right, then from that you can get both the values of the state and what's the action to do given the state you are in. Now if I were to tell you the Q values, did I tell you the transition model? No. So this is like a huge big deal in reinforcement learning. Basically learning the transition model means learning in some sense action representation. Okay, AI 101 says you want to represent everything explicitly. Okay, but the reinforcement learning community says, well, you could if you feel like, and you are some sort of a AI philosophy kind of a person, you feel as if you must represent things explicitly, you can. But if I don't feel like it, I don't have to represent it. I can just learn Q values directly. Okay, and that would then be called model-free learning. If you learn the action transition, then you have learned the model and then used it. If you didn't learn the action transitions, then all you know is long-term expected values of states or long-term expected Q values of state action pairs, which would not tell you what an action would do in a particular scenario. It will only tell you what you should be doing from this state. Okay. Now, as far as learning how to perform well is concerned, if you have Q values, you can learn how to perform well. Or if you have a transition model and the values, you know how to perform well also. So these are competing approaches. So that's why model-free and model-based reinforcement learning algorithms are sort of competing approaches. And they are kind of religious wars. You can't actually say one is right, one is wrong. Eventually you can say in my application, I tried the model-free one, it's not working well, so I tried that model-based one. So to do the model-based one, you need to come up with a representation for your actions first. Okay, yes?
For the Q function, there's an implicit third parameter, which is the goal, right?
Yeah, no, but the point is, you don't need to have goals because we're talking about MDPs. So MDPs are completely in terms of just immediate state rewards. And we assume discounted infinite horizon MDP model in reinforcement learning. Do you understand what I'm saying? So discounted infinite horizon MDP model basically means each state has an immediate reward. Okay, some states may well be sync states, but that's okay. And you can essentially, keep working, and keep collecting rewards, but future rewards are discounted with respect to current rewards. So mathematically, the cumulative reward is always, finite. And it also essentially, at least conceptually, you don't need to say what are your goals. So goals become a specific reward model. Having goals is a specific reward model. Okay, a reward model is way more expressive because in some sense it's like having a Pascal program becomes a Turing machine eventually. But a Turing machine is much more than a Pascal. It can be our Intel assembly language. A Pascal program becomes Intel assembly language program. But Intel assembly language program can also express Lisp programs and Haskell programs and all this other stuff. Okay, so this is really an atomic model, and the atomic reward model is actually quite expressive to consider things like goals and things like trajectory goals, things like you get to get this reward only 5 times, after that you won't get, and all those things can be, you can manipulate them compile them into this atomic model. Okay, so that's basically, so then you really can do this, or you can do this and this, or you can just do this. all of those are ways of doing reinforcement learning. Okay, all of them will allow you to get to perform well from the point of view of MD2. Okay, so the dimensions, in some sense we mentioned the dimensions right now, but so the dimensions of reinforcement learning, one we already talked about, okay, model based versus model free, and I kind of explained to you what's the difference. Okay, the other is passive versus active reinforcement learning. In the case of passive reinforcement learning, in some sense passive reinforcement learning is not the general problem, it's a less general problem. Active reinforcement learning is what we talked about here, which basically means you are just given the, as I said, you're only given the effectors, perceptors and the world. That's all you're given. And you have to learn to figure out how to perform optimally. In the case of passive reinforcement learning, it's actually a different problem. You're given effectors and perceptors, the world, and a compiled policy that's being performed. So there is some particular policy that the agent is performing, or you're hardwired to perform. And and there is no free will anymore. This particular policy is being performed all the time. Okay, all you're trying to figure out, so let's say your friend is performing a policy and you are an outsider and you keep wondering what is this guy's value function. Given the policy they are performing, what is the value they are getting? Which is just, so in the case of passive reinforcement learning, all you would do is try to learn the long-term expected reward for a state, long-term cumulative reward for a state, cumulative expected reward for a state, given the underlying policy. And that's just knowledge, you have that now. Okay, now active reinforcement learning on the other hand, there is no policy being performed. I mean, there is no fixed policy that's being performed. You get to decide what the policy is. Now that's a way more interesting problem because in the beginning you cannot do much more than just randomly pick actions and see what happens. And as you see what happens, you are learning both the state values. I mean, you're getting information to learn state values, you're getting information to learn the transition model, you're also getting information to learn the reward. Because as I said, state rewards are easy to learn, so I don't make a big deal about it. You go there, you feel it, and then you remember it in a table. Right? Okay. So in the more general, in the active case, in the beginning you just get to do some random actions and see what happens. Now suppose after doing a bunch of random actions, you have taken time to figure out what the transition model is. For the actions that you have tried, you have seen where they have gone to. Because you have this memory, right, you keep remembering, okay, I mean, you keep notes. You say, I am in state S5. I did action A1. I got state S3. Tomorrow, I am in state S5 again. I did action A3 again. I now got state S5. So that means A can get either S3 or S5. So with half probability it gets to S3, half probability it gets to S5. That's the best I can do at this point of time. Okay, and if I do that, then I have learned a model of my actions. And as soon as I learned a model of the actions, since I have the reward model already, I mean for the states I have looked at, I can compute the optimal policy. And then I can just keep using that optimal policy. Except the problem is that would be the optimal policy for the partial model. You haven't seen the world. This is the point I was making last time. I mean, you've gone through the elementary school, you've figured out, whatever you learned, and you said, I know all I need to learn, and now I want to exploit my learning. So you make, based on your elementary school knowledge, you make an optimal policy for your life, and you keep doing it. Okay? That would be the optimal policy among all the elementary school dropouts or elementary school graduates, but it may not be the optimal policy you could get if you took more time to learn more about the world. Now the problem, of course, about learning more about the world is there is no end to learning more about the world. I mean, as some of you, at various stages in graduate school realize, right? And so the question is, when do you stop learning about the world and actually put it to use, exploiting it? Okay, so all we know is pure exploitation is stupid, and pure exploration is also stupid, right? Although, of course, a mark of high civilization is they pay people like me just for pure exploration, right? Because other people will do tilling the soil or driving the cars, and some thinkers can think, hopefully. Okay, but that's a different story. Let's not get into that. Although, especially since Republicans have come to power, this might end tomorrow. So we might cancel all the classes for the rest of the semester. But that's a different story. So the question then is passive versus active. In one case, you are just learning the state values. In the other case, you are learning the values as well as the model. Okay, in the passive case, there is no exploration because you don't have any impact in deciding what action to do. You just are a passive observer. In the active case, you get to decide what actions to do. And the active one is the real reinforcement learning. But we will start with this because it's an easier problem and then go here. Yes, sir.
So in the passive model, is it safe to say that if you're like an observer watching somebody else execute a policy, then you're kind of learning what they are doing but not how good it is?
Well, so it's like, the passive model is almost never really useful because you should feel the reward they are feeling. You should feel the reward they are feeling because even in the passive model, you should at least know the immediate rewards. So it's like really the best way, the cleanest comparison for passive model, passive reinforcement learning, is you are born with a particular policy built in. And then unfortunately you also have a brain, and so you are essentially introspecting. So I am in this rat race, what am I getting out of it? But you're not changing the policy. You're just learning how good is each state based on the rewards you are getting in the states that you're going through. Okay, but then if you were to figure this out, then at some point of time you have to start changing the actions. Like that passive reinforcement learning doesn't talk about. Okay, so it's more of a pedagogical tool. It's sort of useful to go from there to the active one. Okay, the other thing we will talk about is whether you are, how you are actually, and this is more of a technical, these two are more technical issues. One, and then it becomes clearer when we go through the actual algorithms. The one of the questions is, you can learn it turns out that you can learn the value of a state in two different ways. You can learn the value of the state by starting from the state, doing an action, look at the next state, do an action, do an action, do an action, do an action, do an action. And then you have a sequence, right? And then you take the cumulative discounted rewards, that is the reward to go from here. So this way you can learn the state's value. This is actually the first idea we'll talk about, called Monte Carlo learning. Okay? But that turns out to be kind of a dumb idea, because suppose later on you might start, let's say this is S1 and this is S2, later on you might start learning the value of S2 exactly this way, right? But then value of S2 is connected to value of S1 by Bellman update, by Bellman equations. Okay? If you have the full transition function, if you have learned the transition model, then essentially you can use the transition model to learn the values of all the related states much faster than without learning the transition model. So one of the questions is, are you doing full Bellman update or partial Bellman update, or are you just depending on the experience? And if you're depending on the experience, there are two ways you can depend on just the experience. One is Monte Carlo, which is, you just keep going until, like you get tired. Okay, let's say it turns out that this is a kind of a world where any sequence more than t long would go through a sync state. Then so any sequence longer than t, it would have gone to a sync state and it just stays in the sync state as you keep doing more actions at that point of time. Okay, so then essentially you can still discount it and take it up, but it depends on the full sequence. The other idea would be to actually say, if I were able to go from S1 to S2, and if I thought S1 is a really good state all this while. Suppose my current value estimate for S1 is 2000. And suppose one day I did an action that I thought was a good action from S1 and I got to S2 whose value estimate according to my current estimates is minus 7000. This makes no sense. Now, this is basically the American housing system, right? In the sense, if your neighbor doesn't mow the lawn, then your house value goes down, right? So you cannot, if you are a good state, then your neighbors will also be good states with respect to the optimal policy, right? And so another thing that you can do in updating the values is to make the values of nearby states more locally consistent. Okay, and that is basically called TD learning or temporal difference learning. Because Monte Carlo and temporal difference are both based on the experience. Okay, in the case of temporal difference, all you're doing is you're actually taking the difference between the two states that you saw and you realize that their values have to be close. In particular, in the optimal case, their values have to be close. They are just connected by the Bellman equation. Okay, so that's the backup can be done by dynamic programming or by experience or temporal difference, for example. Temporal difference or Monte Carlo is another case. And one other thing which we will do is most of our discussion will assume atomic or tabular representations. Okay, so in some sense when I say learn, I'm saying you learn a big table saying S1's value is 7.75, S2's value is 47, and so on. Okay, but clearly if it's any reasonably sized world, there will be too many states, and this way you will take a long time to learn the values of all the states. So another idea would be that these states themselves are described in terms of features, state variables, let's say. So then this becomes a simple classification or regression learning problem. Okay, for each set of features, I give you a number. Another set of features, another number. Another set of features, another number. Find a function that takes you from the space of features to the number. The interesting thing is, in a pure classification supervised learning, both the states, both the examples and their labels are given by the teacher. In the reinforcement learning, you are making the labels for the states by actually experiencing the real world. So you're making the labels for your learning problem, and then you're calling the learning problem, some existing, inductive learner. Okay, so that's basically, we will mostly think in terms of atomic models, but really in the background, when you go to the propositional, when you go to the propositional and relational models, then you have obviously the issue of learning. So you generalize. Okay, whenever you get a couple of examples and you find a pattern, then that's an inductive leap. And that generalizes. That's generalization in the sense, even if you have never seen S57, you realize that the function, according to this function, S57 is basically the same as S42. And so they both will get the same value. Or S57 is like sort of between S42 and S49. So by the regression, you get the value sort of in between. Okay, so if you do that, then you are basically, it's a case where inductive learning becomes a subroutine for experiencing the world. So everything you learn in inductive learning will be used here, except it's just as a subroutine. Okay, so that's basically, so we'll first look at the tabular representations, but we'll also look at some issues of learning factored representations. And one other interesting thing is that in classification learners, there are two types of classification learners. One is batch and the other is online. Batch learners require you to give them all the examples and their labels up front, and they'll come up with a hypothesis that best fits the data. An online learning algorithm basically keeps changing the hypothesis as new data keeps coming. Clearly for us, online would be a much better idea because you don't ever get done exploring the world. So with respect to my current knowledge, this is the best value function I have. Okay? And in particular, actually, when you are learning values in a tabular form, essentially you start off are filling S57, 93, and so on. You're filling different rows for different states. When you are learning the factored form, then it may well be, let's say, that suppose again, remember that inductive learning has hypothesis. Right? You have to decide the space of hypothesis you're going to consider. Suppose you decided to go with linear space, W1 times F1 plus W2 times F2 plus Wn times Fn is the value. These are W's are all the real valued weights, and the features F1, F2, etc. Fn are features. And they could be Boolean, they could be non-Boolean. Okay, then as you see more examples, you will wind up changing. This W1 might go up, this W2 might go down, Wn might go up, so that the overall function you are learning is consistent, closer to all the examples you have seen and their values. So the update rules would be in terms of the weights themselves directly. Okay, so it turns out that once you go into the factored representations, the Bellman updates will be done directly in the space of weights rather than in the space of actual values. Okay, so that's the other thing to keep in mind. Yes?
Just to clarify something, if we're in one state, say S0, we perform an action A, and I can take us to a state S1 with, for example, high reward, or it might take us to a state S2, which might have not so high reward. We kind of learned that the rewards are correlated with performance of the action, not caused by the action necessarily. Or is it a causal link between the two?
No, there is no distinction at all being made between causation and correlation. It's just a question of when you do these actions, you're getting into these states, and these states have these rewards. Okay? So remember, remember that, this is nightmare for AI people, and even more of a nightmare for logic AI people, because these are people who are saying we don't even need a representation. We should be able to just learn Q-value functions. And if they learn the Q-value functions, you won't ask me, are they learning causation or correlation? Who cares? If I do this, I feel good, so I'll do it. That's it. Right? Is my doing it making me feel good or not? I don't care. I just know that if I do this, I feel good. Okay? And so in some sense, it allows both the representation-oriented people and the people who don't like representation.
So
okay?
There's an underlying assumption that we're making that the only changes in the state of the world are due to the actions we ourselves perform.
This is again basically the entire MDP and POMDP models we have looked at. MDP model basically assumes single agent, stochastic world. That means the other agents are not being modeled. Their effects are modeled only as stochastic effects of your actions. If you want to model the real world that we live in is actually a multi-agent POMDP, DEC POMDP. And you're learning, you're doing reinforcement learning in a DEC POMDP. which is exactly why when you fall into Grand Canyon, I get to learn. Okay, but we are not doing that. We are talking about single agent, fully observable single agent reinforcement learning to get an idea of what the issues are. Okay. Okay, so passive learning. So basically what we'll do is we will first do passive learning and then do active learning, assuming model based. That's the way we'll go. And then we will look at the model free version of both passive and active learning. Okay, and then we can look at the generalizations. Okay, so let's look at the passive learning. And in fact, in the case of passive, the simplest way of doing, so as I said, the simplified task is you don't know the transitions, you don't know the rewards, but you will feel it when you get there. Okay, I mean, so that not knowing the rewards has like two aspects to it. One is you don't have it listed in your memory. But if you are a depressed individual, even when you get there, you won't know it. That means you don't feel the reward. Okay, but that we would assume that is not the case. Our agent is not depressed. Okay, when it goes to the state, it will feel the reward. Okay, it's fully observable both in knowing the state of the world and knowing the state of the reward. Okay, and then you are being given a policy pi. So your dad or mom told you, just do these. Okay, so this happens, in the beginning when you start going to school, they'll say, do this, do this, do this when you get to school. And, if you have brain that you're, and that's kind of taking a step back and saying, so my mom asked me to do this, I am doing this and I'm feeling these kinds of rewards. So exactly what states have what long-term reward? So for example, why do people learn to hate Mondays? When you were a kid, did you learn to hate Monday? No, because all days are equal for you. You just kind of, hang around doing nothing. And then over a period of time, you realize that Monday is the beginning of the bad school stuff. And so you start saying long-term reward for Monday is quite negative. Whereas long-term reward for Fridays is better because that has, a weekend coming. And the long-term reward for end of May is good because summer is coming and you don't have to do anything. These things you learn. You didn't decide your policy when you are a kid. Right? You follow instructions from your parents. But you still learn, long-term valuations of states. And then after a while, you actually start using your brain to change actions, and then we call you a rebel. Because you're not following the policy we gave you. Right? And then, bad things can happen, such as, you drop out of Harvard and start Microsoft and things like that. Very bad things. But anyway, okay, so passive learning, you've been given a policy and you're just following that policy, and then you basically try to learn the state values. Exactly like you kind of figure out that, hey, Mondays seem to be kind of bad deals. Fridays seem to be kind of good deals. Okay? And that's what you are trying to learn. And you don't have a choice as to what actions to take because people are telling you. And when you take an action, the outcomes are not always specific because there may be certain Mondays when you go to class and there'll be an excursion. Fun, fun, fun. And then another Monday you go to class and there's a big exam. Bad thing. Okay, so immediate rewards change because there are multiple things that can happen on a Monday. Okay, so based on, and by actually doing it in the world, you experience the rewards, and then you will eventually figure out what is the expected reward starting from this state. Expected cumulative reward starting from this state. Okay, yes sir?
But for this passive learning, you're not updating any policy whatsoever.
No, you're just following the policy.
So you're not making any use of this knowledge?
No. But it's sort of, your brain has now. You started hating Monday, that's, for example, that's knowledge now. There was no reason to hate Mondays before. Okay, and similarly, and also there was no reason to stay away from spouse even when you are a kid. Right, but you learn those things. Okay. So, but then the next step is after, just a second, next logical thing is after learning the state values, you want to convert into an alternative action. You're not the first kid to say, Mondays aren't good, let me not wake up on Monday so that Sunday will continue. My kid does it all the time, right? And then we say, what a rebel you are, and pull him up and take him to school. And then when they become really big, you can't do it, okay? But that's part of being an intelligent agent. You want to convert it. Of course, I will tell him this whole exploration trade-off and say that you need to, the dad knows best because he has explored a lot more than you, etc. But anyway, yes, that's your question.
So, while performing the policy that you're given, what's constantly getting updated is your reward function for each state.
Yeah, whenever you go into that, that's definitely you are learning those.
Okay.
But that just goes directly into the table. And in fact, notice that reward functions too can be learned inductively. In the sense, you could basically say, in the features, states with the following features seem to be giving me more reward. Things that seem to have plastic wrappers around them, seem to be candies, and I eat them, I get this rush of sugar, so more reward. Things like that. Okay, so you would then start seeing anything wrapped in plastic wrapper, you'll try to put it in your mouth. That's what you do. If you didn't do it, then obviously you're not a human kid. That means you didn't generalize. If you didn't generalize, you won't be here. You have to generalize, because if you just did only the things that the experience taught you exactly, it never gets repeated again and again. We always implicitly generalize. And so, with generalization comes bad generalizations. Okay, so that's the thing, and that's a simple problem. And so one simple way of doing this, if you did not know anything else, is this, Monte Carlo. Starting from a state, you remember, okay, starting from the state, okay, today is Monday, and I'll do this. And then back it up, and compute the value you received for Monday. Okay, so for example here, starting from the state 1,1, I followed my policy. Okay, and starting from state 1,1, I followed my policy. I went up, right, up, right, exit. Okay, and then I was done. In this case, again I did up, and then of course somewhere I got into a different state, so I did follow the policy from that state. Remember, a policy looks at the state and decides the action, whereas a conformant policy just says if it is fifth action, I'll always do A5. Right? Okay. So this is what I did, following this policy, and then I got total reward here, which is 92, and total reward here, which is minus 106. So I have two examples. So the average reward I'm getting in 1,1 is 92 plus minus 106 divided by 2. So that's minus 7. You see what I'm saying? Okay. So and similarly now, as you see U11 more and more often, you will get better and better idea about its true value. Obviously, this is just learning from two examples. If you visit a state infinitely often, then eventually you know that this will converge to the true values with respect to the policy. Agreed? Okay, it's a very simple thing. It doesn't look like, calling it learning looks like an insult, right? Because you are just, but unfortunately rote learning is learning. Right? Basically hitting yourself with the same hammer multiple times shows you don't learn. Right? So, at least you have used your memory to keep the experience. That's the beginning of learning. Okay, and then you average it out in this case. Now, of course, if you want to do a little more and say, well, maybe the valuation of U11 really can be written in terms of the features of U11. Right now, these are all black box. The evaluation of state 1,1 can be written in terms of the features of the state 1,1. Okay, and maybe I can talk about features such as it's a corner state, has two neighbors, things like that are the features now. Okay, and then I can say that basically it's not that 1, 1 gets this minus 7 as the label, that being in corner state and having 2 neighbors, etc. is giving me minus 7. So with respect to this representation, now I can learn a function which directly takes me from the features to the value. Now notice double whammy here. First of all, the labels could be wrong. Even for the individual state, the labels could be wrong. Because you didn't really experience 1, 1 enough number of times to be sure that minus 7 is actually its long-term reward, long-term cumulative reward. And then, as if that wasn't enough, you're generalizing on top of it. So you get even more errors. But what else can you do? If you don't, then you will say, I will wait before doing anything. That would be too late. Okay? So, inductive learning over direct estimation, states can be represented in terms of features. The long-term cumulative rewards experienced from the states become their labels. These are in some sense noisy labels, because whether or not the labels are correct depends on how long you actually have. How accurate they are depends on how many times you have behaved from that particular state using the same policy. Okay? And then you can do inductive learning, regression, to find the function that maps the features to the values. And this generalizes the experience beyond the specific states you saw. And in fact, good inductive learning might even say that the states that you actually saw, it may not agree with the things that you found there even. Right? Because, a classic case of inductive learning, right, is, curve fitting. A classic case of regression is curve fitting. These are the points I have actually observed. For these x values, these were the y values. And I have decided this is the function. So this function doesn't even agree with this actually observed value or this actually observed value. But that's okay. It's the best fit because it's least distance cumulatively from all the observations. So this is the entire learning thing, just comes lock, stock and barrel through the back door into reinforcement learning. So reinforcement learning is a more general kind of learning than just classification, where somebody told you what to learn over. Here you made your own learning problem. You notice that, right? You made your own learning problem. Okay, so that's, of course, going back to the direct information from the atomic level, let's think about what's wrong with it. I mentioned it already once. What's wrong with it is it's highly inefficient. Well, you can say, well, everything is inefficient. You're saying infinitely often you will get accurate. How efficient can you get? Well, the question is, you don't have to be. Just because of that, you should not just, you shouldn't do redundant work. And the redundant work you do here essentially is you don't realize basically what you're doing in doing this is we are basically computing the value of this policy. Remember we talked in the policy evaluation, you convert the policy into the value function, and then given the value you get another policy, then convert that policy into a value function, and there is a policy evaluation step. This is empirical policy evaluation. This is actually doing the actions to evaluate the policy. This is one way of doing the evaluation of the policy. But it's a very inefficient way because it misses the point that the values of the neighboring states, where neighborness is defined in terms of the actions, are highly correlated. The right thing to do, then, the way you actually computed the policy evaluation in the policy iteration, is to set up a set of linear equations which connect the utility of a state to the utilities of the states you reach, the expected utility of the states you will reach. So if you are in this state and you are doing this action, then with 0.8 probability you will be in this state, 0.1 you will be in this state, and 0.1 you will stay in this state. In this model, remember? And so then basically u of this state is 0.8 times u of this state plus 0.1 times u of this state plus 0.1 times u of this state. You get a bunch of linear equations, you solve them, you get right away utilities of all the states. It uses the same experience to a much better degree. And all of learning, the difference between a good learner and the bad learner is what? How efficient you are in using your experience. All of you went through the same schooling system, more or less. Okay? If you're a better learner versus worse learner, it's a question of what did you do with that experience. And the Monte Carlo one is basically using that experience in a pretty, it squanders that experience because it's not considering the correlations between the states. And this one actually uses the correlations. But to be able to do that, you need basically just do the dynamic programming based policy evaluation. Just direct policy evaluation. The thing that you need to do that is what? Remember I just said u of this is 0.8 times u of this plus 0.1 times u of this plus 0.1 times u of this. What are those numbers coming from? Where are 0.8, 0.1, 0.1 coming from? That's the model. Okay? See, just because you're doing this, all you know is your dad told you or mom told you if you are in this state, you do this action. If you are in this state, you do this action. That's all your mom or dad told you. Okay? They didn't tell you that when you do this action, when you go to school, sometimes you'll get to a school with a happy teacher, sometimes you'll get to a school with a kind of a cranky teacher. And those are, with stochastic different probabilities, that can happen. Okay? And you are essentially trying to learn that through your experience, in addition to just learning the values. And so the argument that we are making now is passive model-based learning, where in order to compute the values of the states, rather than directly compute the values of the states, which is what the direct estimation was doing, I do an indirect method. I compute instead the transition probabilities of the actions, which is I compute the model with respect to the policy. Okay? So, and when I compute that model, then as soon as I have the model, I can then use the policy evaluation with respect to that model and the rewards that I know already. Okay? To compute the values. And that is essentially called adaptive dynamic programming. Because it's called adaptive because you are learning the model. So you're adapting the model to be correct, consistent with the experience. And then you're throwing it into the dynamic programming equations to compute the values. Okay? That way, in one fell swoop, you'll get the values of all the states. And in the textbook, they actually show pictures of the convergence rate, of values of the different states to their true values in terms of, for the ADP versus Monte Carlo. And you'll essentially see that always a bad learner is the one which sort of goes slowly and might even not reach full accuracy. Monte Carlo actually does converge to the full accuracy, but it goes very slowly. Its learning rate is extremely slow. ADP, on the other hand, has a much faster learning rate. Okay? And so that's basically the model-based learning. And to be able to do that, all I'm doing is now I'm looking at the same experience. I'm looking at the same experience. Except instead of just adding all of these up and dividing it by the 2 to get the values, I'm actually looking at these as each experience episode is really many, many little episodes of doing an action from a state. Okay, so for example, if I am doing, let's consider 3-3. Okay, if I consider 3-3 and I did right, I got to 3-2 here. 3-3 I did right, I still got to 3-2 here. Did I? Here I did 3-3 and right, I got to 4-3. You see what I'm saying? So it looks as if I do right in 3-3, I get to 4-3 with 1/3 probability. Because of the 3 times I did, 1 time I went into that state. According to my knowledge right now. You see it? Okay? So once you get this, I got the model, now I throw it into the DP equations. I didn't even show it here, but you know what the DP equations are. It is like U of the state is gamma times 0.8. Gamma, U of this state is reward of this state plus gamma times whatever is the transition probability for doing this action and getting into this state times the U of this and so on. There is no max here. Remember, policy evaluation is a happy thing because we just get linear equations. Okay, so it's again the beauty of this. I mean, the number of things you can say about reinforcement learning and real life analogies are just unlimited because essentially